Okay, our next introductory topic before we get to what's in the lecture manual is in calculus. We will want to find the area of a polar region, which is based on the area of a sector of a circle. There are two main concepts you must master for this task: finding the continuous interval over which the region is formed and finding the intersections of two polar curves. So these are two ideas we're going to address. Now, again, in pre-cal, you should have done some work with polar coordinates, but there's no telling what you remember. So we're going to look at a graph. Now, I'm going to unveil this graph. Find the area of one petal of 3 cosine 3 theta. This is going to be what we want to do. So first we have to find a continuous interval over which one petal is formed. Now, if you look at your polar graph, you can see here is 0, pi over 2, pi, 3 pi over 2. Here is pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, pi over 6, 5 pi over 6, 7 pi over 6, 11 pi over 6, pi over 3, 2 pi over 3, 4 pi over 3, 5 pi over 3. We have an extra little increment in order to make all this even, and that would be pi over 12, which we know pi over 6 is 30 degrees. So pi over 12 must be 15 degrees. So if I count off in 15-degree units, we can kind of see what's going on here. Okay. Also, we're going to let each one of these circles that you see, we're going to let every 2 of them be a length of 1 on our radial axis. Okay. Now, you may be sitting here looking at how do we get that curve? Well, our equation is 3 cosine 3 theta. So if you know nothing else, you know you can make an r theta chart. Okay, so that means we're going to pick our theta, and we're going to take 3 times the cosine of 3 theta to get our radius. So I'm going to show you my chart I came up with. So in order to lead you through this, I am going to do one part at a time. 0. 3 cosine 3 times 0 is 3 times cosine 0. We know cosine of 0 is 1. 3 times 1 is 3. This means on the radial arm here, where the angle 0 is, I'm going to go out 3 units. There's my point. And so my next unit circle value that I know is at pi over 6. 3 times cosine of 3 times pi over 6. Guess what? 3 times pi over 6 is pi over 2. Now, I know cosine of pi over 2 is 0, so at the pi over 2 radial arm, I'm at 0, so I'm at the pole. How do I know that the graph did this? I need an intermediate angle. So what is between 0 and pi over 6? Pi over 12. So let's substitute pi over 12, so that's 3 times the cosine of 3 times pi over 12. Which gives us 3 times the cosine of pi over 4. Well, I know cosine of pi over 4 from my unit circle is square root of 2 over 2. Square root of 2 is about 1.4, so 3 times 1.4 is about 4.2. Divide by 2 is about 2.1. Close enough at pi over 12, which is right here. I'm going to go out on this radial arm 2.1. So on this thing, 1, 2, and very close, just a little bit bigger. Now I can see from here to here to here. Well, let's continue. At pi over 4, 3 cosine 3 times pi over 4, that gives me cosine of 3 pi over 4 is negative square root of 2 over 2. 3 times that gives me negative 2.1. Well, at pi over 4, that's this radial arm. And negative 2.1 on this radial arm would actually take me down here to that point. So now I have this point, this point, this point, and this point. So pi over 3. That's 3 times the cosine of 3 pi over 3. The 3's cancel, so I have 3 times the cosine of pi. We know the cosine of pi is negative 1, so 3 times negative 1 is negative 3. So at pi over 3, on this radial arm, I'm going to go negative 3. So instead of plotting my point this way, I'm going to be on the line that goes through pi over 3, but I'm going to go in a negative radius. There it is. So now I see this much. So you're beginning to see it develop. At pi over 2, I get 3 cosine of 3 times pi over 2. 3 pi over 2 has a cosine of 0. 3 times 0 is 0. So at pi over 2, I'm back at 0. Okay, so I need this point. So that would be on the 5 pi over 12. Notice that that would be between pi over 3 and pi over 2. So 3 cosine 3 5 pi over 12. 3 goes into 12 4 times. Cosine of 5 pi over 4. Cosine of 5 pi over 4 is negative square root of 2 over 2 times 3 gives me this, negative 2.1. So on my 5 pi over 12 radial arm, I'm at negative 2.1. There we go. There's a pedal right there. Notice at pi over 6, I had a point at the pole, and I got back to that point at pi over 2. So I get one pedal from pi over 6 to pi over 2. And I could integrate this function on that interval and get one pedal. And if you wanted to, you could continue this process until you get one entire graph of this. But what's interesting is we get the whole graph in pi units. If you want to keep writing all this down, we get the full graph from 0 to pi, the full thing. That means what's going on from pi to 2 pi. Guess what? It's going to repeat itself. So if you want to copy this part down. All right. This is very laborious, so it's nice if we can actually have some more thoughts on what is actually going on. So let's get those calculators out. Okay, I have several functions pre-written in here. I'm going to look at this one, okay? And I'm going to go to my y equals, and I'm going from 0 to 2 pi, and I'm going to let my t-step be, I believe that might be pi over 36. Pi divided by 36. Yeah, okay. And you can see my window. I'm going to double the length on the x-axis that I do on the y-axis because my ratio is 2 to 1. Now I'm going to go back to my equation. It's very important. You want to always be in path mode so you can have a good understanding of what's going on. All right, watch the graph. Oh, my window's not big enough. Okay, let's look at the graph again. It goes very fast, doesn't it? Okay, so I have always want to check the path, have it on path. Let's look at what happens here. And it goes right back over itself. I have it graphing from 0 to 2 pi. So what that means is I get one full picture there from 0 to pi. But when do I get my leaf, one petal, we call that? If I trace, there we go. There is my theta is an approximation, but we know that that's going to be at pi over 6. Oopsie. And pi over 2. Okay, now, we now could find the area of one petal. And it really doesn't matter if we do it this one or this one or this one. They're all going to be the same size. But you know what? We need a better understanding of what these graphs look like. So now go to your lecture manual on page 139. This is a wonderful worksheet done by another teacher whose name's at the bottom of the page. It's really good. Okay, here's what it says. We are going to take our calculator and we're going to be in polar and radian mode and graph the following equations. So 2 cosine theta. So I'm going to turn this graph off. 2 cosine theta. I'm going to turn that one on because I've already entered it. We're going to confirm that we are on path. And I'm going to graph it. So let's double check that window. The window was -6 to 6 with my scale being 1 and -3 to 3. Looks like a circle, doesn't it? Centered at 1. Radius of 1. That is quite interesting. Diameter of 2. Let's sketch this in. For the purposes of this picture, I'm going to make this my center, and that means that this is going to be 2 units right here. This is 1, so that makes this 1 unit and 2 units. Try to keep everything nice and simple. So I had a 0 there, and then I came up here, and here's -1. So here is my circle. And of course, I wouldn't have that point on the graph. I could have a better window, but here's what's interesting. This reflects across the x-axis. Okay. Let's turn that one off. And let's look at 2 sine theta. Turn that one on. Enter that in your calculator. Again, I'm going to make sure I have my path. I do. And I'm going to go ahead and graph it. Huh. And look at that. It also goes around twice, just like the cosine one did. So this one looks like this. Notice this is going to reflect on the y-axis. So let's do another one. So let's look at -3 sine theta. Again, I want to confirm I'm on the path. I'm good. Okay. Oh, look at that. Diameter of 3. I'm going to go down here to 3. Okay. That means my diameter is 3. Here would be where my center is, and I want to go 1.5 this way and 1.5 this way to get a nice picture. But there it is. Now, interesting. Now I know we graphed -3 sine theta, but look what it did. Here's 2 sine theta. That's a diameter of 2. -3 sine theta has a diameter of 3, but it's down here. Interesting. So you're going to finish these graphs out. Let's look at the next one. 2 plus 2 cosine theta. Well, that's interesting. Turn this one off. Turn that one on. Again, confirm that we are in path mode. We are. All right, let's have a look at this one. I don't know if my window's good yet. I'll look at it after I've graphed it. Okay, let's look at the graph of it. It's hanging out there for a little bit. Okay. Well, that's interesting. First of all, it took all 2 pi for it to graph. But also, if I turn it this way, it kind of looks like a heart. This is called a cardioid. But interesting that it has a little indentation. All right, and again, each one of these is 1 unit. So I'm going all the way out to 4. Okay, and this is intersecting here at 2 and -2 and coming here. So I have this and this. That's good enough. So interesting things are happening here. So again, you're going to graph the rest of these and then answer some questions. Okay, let's look at 2 cosine 3 theta. We already did 3 cosine 3 theta, so we kind of know what to expect. So here's your graph for that. We know what to expect. It's repeating over itself, so that's interesting. All right. So again, you're going to finish this page, and we will look at the solutions to these in the next class. Okay, so after working through all of those other problems, you can see that you can come here and do a point-by-point sketch of these graphs that are on this page. You might want to do that. It would be good practice for you, especially since last year you probably didn't have enough practice with polar coordinates. Okay, so that would be a good thing to do. All right, and now we are ready to go to our lesson on the polar coordinates and calculus section 10.4.